All right, welcome back everyone. The topic for today is complex numbers as vectors. So it turns out to be helpful sometimes to be able to visualize what's going on with complex numbers. And so it turns out we can represent complex numbers as vectors in a really nice way, which gives us a way to think about complex numbers geometrically, which is sometimes helpful. Although, admittedly, we're going to spend most of this class focusing more on analytic and algebraic properties of complex numbers, but every once in a while you can get some intuition from thinking of things this way, so it's worth having on hand. So the first little definition we'll talk about is the modulus of a complex number. So if you're thinking about a complex number as a vector, first of all, so in this upper left picture here, you can see I have this vector pointing at z equals x plus iy. So that means that the head of this vector, the terminal point of this vector is at x comma y, of course, because we can think of the complex number z as the point x comma y, right? So we can think of that as a vector originating from the origin. And then the modulus of the complex number is just the length of that vector. So it's just how long this arrow is here. And it's not hard to see that if you know the distance formula, that the modulus of z, which we indicate as the absolute value, is the square root of x squared plus y squared. It's just like you're measuring the distance from x comma y to 0 comma 0. So that's a formula that we need to know. Let me highlight that there. When we sum two complex numbers, the easiest way for me to think about it is if I want to do z1 plus z2, that just means that first do z1, and then from the endpoint of z1, then do the vector z2. So in this picture that I have on the top right here, starting from the end of z1, if I would make a copy of z2, so this is a copy of z2 here, then the sum is this vector in red. You can also think of it as starting from the end of z2 and then doing z1 from there. Some people talk about the parallelogram rule, so the vector in red is the diagonal of the parallelogram spanned by z1 and z2. But for me, it's easier to think, just do z1, and then from the end of z1, do z2. Then we can talk about negation of a vector. I mean, it's just if you've taken linear algebra or some class like that where you deal with vectors, it's the same idea as it was then. So if I negate z geometrically, it's just the same length vector pointed exactly the opposite direction. So this angle is pi, right? And then to do the difference of z1 and z2, well, an easier way to think about it is instead of thinking z1 minus z2, think z1 plus negative z2. Well, we just talked about how to negate a vector. So if I did negative z2, that's like here. But since we're talking about vectors, I can, if I want to do z1 plus negative z2, I would go to the end of z1 and then do negative z2. So it'd look something like this. And then wherever the endpoint you end up at is the vector z1 minus z2. So this would be z1 minus z2 here in green. So there's z1 minus z2. But it's often more convenient to think about it as going from the tip of z2 to the tip of z1. So this vector right here is also z1 minus z2. And what's cool about looking at it that way is that it becomes clear that the magnitude of z1 minus z2 is just the distance from z1 to z2. So here at the bottom, I want to emphasize that. We'll take advantage of that property a little later. And, since we're talking about complex numbers form a plane, we can certainly have curves in the plane, like a circle, for example. You can have parabolas, ellipses, all sorts of things that can easily be described in terms of equations involving complex numbers, which is really cool. I'm just going to give you just one example of this here, the equation of a circle, because circles are kind of important. So I want an equation that if an arbitrary complex number satisfies that equation, that means that that arbitrary complex number was on the circle. So here's a circle that's centered at z0 with the radius r. So if I have some arbitrary point here, let's just say z, on that circle, what equation must z satisfy? Well, if you're on a circle centered at z naught of radius r, that means that the distance from z to z naught is exactly r. But we know how to calculate the distance from one complex number to another. It's just the modulus of the difference of those 2 points. So the equation of this circle here is the modulus of z minus z naught, that's the distance from z to the center of the circle, has to be equal to r. With this notation, the equation of a circle becomes extremely simple, right? What we find in the complex plane is that a lot of phenomena that we've modeled with equations and functions, say in calculus class or something like that, become simpler when they're expressed in terms of complex numbers. Let's talk about some of the algebraic properties of the modulus. The first one here says that the modulus of z squared is the real part of z squared plus the imaginary part of z squared. Just a little reminder up here at the top somewhere. If we have z is equal to x plus I times y, then we know that x is the real part of z and y is the imaginary part of z. So if I wanted to verify that first property there, I could just say, well, let z equal x plus I times y. Then the modulus of z squared, well, we know that the modulus of z is the square root of x squared plus y squared, and then we're squaring that. So that just ends up being x squared plus y squared. But x is the real part of z, so we got the real part of z squared, and y is the imaginary part of z, so we got imaginary part of z squared as advertised. The second property is something that's kind of useful to keep in mind, comes up every once in a while. So the real part of z is always less than or equal to the absolute value of the real part of z, which is in turn less than or equal to the modulus of z. So we're using the same symbol here, but in 2 different contexts. So here the absolute value symbol means absolute value, right? Because the real part of z is a real number. But here it's modulus, so it's a different concept. It's the same symbol, but different concept. Now, when we're talking about real numbers, we go up here to the margin somewhere at the top. For every real number, it's the case that x is less than or equal to the absolute value of x. So this is true for every real number x. So this is just something that we can assume is true because it's just a property of real numbers. Every number is less than or equal to its absolute value, which is not surprising because when you take the absolute value of a real number, if that number is positive, you just leave it alone. And if it's negative, then you make it positive so you get something even bigger. So this first inequality is just for free because it's a property of real numbers. So it's really the second inequality that we might want to establish. Absolute value of RE, the real part of z, is just absolute value of x. But another way to write the absolute value of x is the square root of x squared, turns out. This is another thing that we get from just knowing properties of real numbers. The square root of x squared is exactly the absolute value of x. But then this is certainly less than or equal to, if I took that inside that radical, I took that x squared and then added something non-negative to it. This just makes it a little bit bigger. And the same trick works on the other side with the imaginary part. So this is just similar over here on this side. And then here's the big kahuna, the triangle inequality. So the triangle inequality says that if you take any 2 complex numbers, z1 and z2, and then take the modulus of the sum of them, it'll be less than or equal to the sum of the individual moduli. This is going to be proven as a homework problem, so I'm not going to give the proof here in the lecture, but the textbook outlines the proof pretty carefully, so basically you're just filling in the gaps in the proof that the textbook is going to give, so you don't have to come up with it completely from scratch. I would like to mention why it's called the triangle inequality. You've probably seen the triangle inequality, especially if you took real analysis before you took this class. You use the triangle inequality all the time for real numbers. It's the same inequality just with real numbers instead of complex numbers. But when you're in the real numbers, it's not entirely clear why it's called the triangle inequality. But when you're talking about complex numbers, it's really clear why it's called the triangle inequality, because it just captures the idea that the sum of any 2 legs of a triangle, or any 2 sides of a triangle, is longer than the third side. Or another way to think about this is that the shortest distance between any 2 points is a straight line. to see how the triangle inequality relates to complex numbers, like let's just make a triangle here. Because I want this to be complex numbers, I put the origin where that lower left corner is. If I call this bottom side of this triangle, let's say it represents, this is z1, and then this vector over here is z2, then we know from the way we do vector sums that this side over here would be z1 plus z2. Now, of course, I realize that z2, if you graph the point z2, it would actually be over here somewhere, like this, z2. But since we're thinking about it as a vector, we can sort of scooch it over here to the end of z1 to form that sum. So anyway, you can see what's going on here is that the sum of these two sides of the triangle has to be longer than this third side over here. So it really is a triangle. They called it the triangle inequality for a good reason. And then there's an inequality that's commonly called the reverse triangle inequality. Usually, if you would Google the reverse triangle inequality, it would give you this second inequality right here, but both of these inequalities are really just kind of saying the same thing. You can kind of think of this, if you want to think of it as in terms of triangles, it says that any side of a triangle is longer than the difference of the other two sides. So I want to prove this one. Kind of got a cute proof. But before I go about proving it, I want to remind you of a preliminary fact about real numbers. Anytime that you say that the absolute value of a real number x is less than some constant c, it means the same thing as saying that x itself without the absolute values is between negative c and positive c there. So if you want to prove the absolute value of something is less than a number, it suffices to prove two inequalities, this compound inequality over here on the right. And so I'm going to use that to prove this first inequality up here, because on the left-hand side of that, I've got the absolute value of something is less than or equal to something else. So we're going to show that this modulus z1 minus modulus z2 is less than or equal to the modulus of z1 plus z2. So we're sort of showing the right-hand side of this inequality that I circled in red applied to inequality 1 at the top there. Okay, so how do we show that? Well, there's a little trick. Start with the modulus of z1. That would certainly be equal to modulus of z1, and then I'm going to add a well-chosen 0, plus z2, and then a minus z2. And I'm going to put grouping symbols in here just to make you focus on what I want you to. So inside that modulus, I've got really a sum of two things, z1 plus z2 and then negative z2. So I can apply the triangle inequality that we talked about earlier and say this is less than or equal to modulus z1 plus z2 plus modulus of negative z2. Then I'm just going to add that modulus of negative z2 to both sides to get this. And then lastly, when you've got just a negative inside the modulus like that, you can get rid of it. You can verify that for yourself. It's pretty easy to check out. Okay, so that proves the first half of this thing. So the next thing we need to show is we need to show that negative absolute value of z1 plus z2 is less than or equal to absolute z1 minus absolute z2. So the way we're going to do that is very similar to what we did in the first part. So if we start with modulus z2, we can write that as modulus of z2 plus modulus of z1, or inside the modulus we can write z2 plus z1 minus z1. And then we can do the same trick with the triangle inequality. So we can write that like this. So we can say less than or equal to here. Modulus z1 plus z2 plus modulus negative z1. But we can get rid of that negative there, so I'm not worried about that. So then you end up with, when you add the modulus of z1 to both sides and get rid of the negative, you end up with modulus z2 minus modulus z1 is less than or equal to modulus z1 plus z2. And then I'm going to factor a negative out on the left-hand side and write that inequality this way. And then you may remember whenever you have an inequality and you multiply both sides by a negative, it reverses the inequality. So from here, we end up with modulus z1 minus z2 is greater than or equal to negative modulus z1 plus z2, which is what we wanted to show, just written in the opposite order. So now we have, okay, this inequality that we just proved a second ago is negative z1 plus z2 is less than or equal to modulus z1 minus z2. And then in the part A, we proved that modulus z1 should be plus, there's a sign here somewhere. Oh yeah, it should have been a minus up here. Anyway, fixing that mistake, that was less than or equal to modulus z1 plus z2 in the middle there. And since the expression in the middle is bounded by the negative of something and the positive of something, that tells you that the absolute value of that thing in the middle is less than or equal to the thing on the right. And that's what we wanted to prove right there. And then once you've established the part A, or the first part up here at the top that I've got underlined in red, the second part follows immediately just by substituting like negative z2 in place of z2 in the first inequality. You know, the negative just goes away on the left-hand side. So 1 implies 2 is easy. So once you've established part 1, getting part 2 is kind of a freebie. One thing you might challenge yourself to do is to understand how this, think about how this applies to triangles. Like, why is it called a reverse triangle inequality? And how can you interpret it as any side of a triangle is greater than the difference of the other two sides? Okay, here's a little example that we can use as an application of that reverse triangle inequality. So I've got a little picture up here. I've got an arbitrary point z on the circle. This is just the unit circle. The unit circle has equation modulus of z equals 1. So in other words, the unit circle is the set of all complex numbers z whose modulus is 1. Those are just the points that are 1 unit away from the origin, so unit circle. I've got an arbitrary z on that circle, and you can see a dotted line from that z to the number 2 on the x-axis there. So from looking at that picture and thinking about all the possible places z could be on that circle, what's the closest point? Like, what's the closest distance, in other words, what's the smallest distance between z and 2 possible among all the points on that circle? Well, in other words, if we think of 2 as a complex number, we can talk about the distance from z to 2. So this distance right here would be modulus z minus 2, right? So what's the smallest that distance could be, is what I'm asking. Well, the smallest that distance could be would be 1, if z were right at the point 1. So 1 is the lower bound on what z minus 2 could be. And on the other hand, what's the biggest that distance z minus 2 could be? Well, that would happen whenever z is over at negative 1, right? And then in that case, the distance between z and 2 would be 3. So it also appears, just by looking at the picture here, that absolute z minus 2 has to be less than or equal to 3. Hopefully that seems geometrically evident from the picture. But what I want to do is just use that reverse triangle inequality just to establish it without having to think about it geometrically. For the first part, I think we can use the reverse triangle inequality there, and we can say, well, modulus of z minus 2, we know has to always be greater than or equal to the absolute value of the modulus of the first thing minus the modulus of the second thing. But what is the modulus of z if it's on that circle? Well, if it's on the circle, modulus of z is equal to 1. So we can replace modulus of z by itself, which is 1. So this becomes modulus or absolute value of 1 minus 2. In other words, absolute value of negative 1 equals 1. So this establishes that first observation that we saw up there, that absolute z minus 2 has to be greater than or equal to 1. And then the second one's even easier. We can use, instead of using the reverse triangle inequality, we can use the forward triangle inequality. Modulus of z minus 2, we know by the triangle inequality, is less than or equal to modulus of z plus modulus of negative 2. Again, modulus of z is equal to 1, since z is on the circle, so this is 1. And then absolute value of negative 2 is 2, so this is 3. So there we have that second inequality. And we arrived at those in a completely analytical way, right? Didn't have to think about that picture. You know, one thing, you could even go into these inequalities that we did on the previous page, and you could put an extra inequality in on top of them. You could write that, for that first one, you could say that's less than or equal to absolute z1 plus absolute z2. For the second one, you could also write less than or equal to absolute z1 plus absolute z2. If you're interested in, you know, the modulus of z1 minus z2 or the modulus of z1 plus z2, you know upper bounds and lower bounds for both of those. You get the upper bounds from the triangle inequality and the lower bounds from the reverse triangle inequality. Next, we can talk about the generalized triangle inequality. So if you're summing 3 or more terms, it turns out that the triangle inequality generalizes, just in the nicest way possible here. The proof of this is pretty straightforward. It's a straightforward induction. Remember, when you do induction, you've got to establish a base case. In this case, the lowest value of n for which this statement is claimed is when n is equal to 2. Well, when n equals 2, what we're talking about is modulus z1 plus z2 is less than or equal to modulus z1 plus modulus z2. That's the triangle inequality. Which, let's assume that we've already proved that that's true, since that's one of your homework problems. And then for the inductive step, you want to suppose that that inequality is true for some arbitrary k being bigger than or equal to 2 here. And then you would consider sort of a k plus first case. Then if you would look at modulus z1 plus z2 all the way up to zk plus 1, well, you could just think of that this way. Think of it as the modulus of z1 plus z2 up to and including the kth z plus, then you get the zk plus 1. And then you can apply the regular triangle inequality, the base case, to this, and it would be less than or equal to z1 plus z2. Just break this up into 2 moduli. So this is by the base case. The first term here in the modulus, you know, this modulus of z1 plus z2 up to zk, falls under the inductive hypothesis. We've assumed that the inequality at the top is true for arbitrary k. So I can write this as absolute z1, or less than or equal to absolute z1 plus absolute z2 plus all the way up to absolute zk, plus then I still have that last term there. So going from this bit is less than or equal to this bit is just the inductive hypothesis. And anyway, that's what we wanted to prove, right? So we just showed that if it's true for the kth case, then it has to be true for the k plus first case, which it is. So there you go. And then we have a whole lot of identities that involve moduli. We're just going to talk about a couple to begin with. So the first one is just that when you take the modulus of a product, it's the product of the moduli. And then you can kind of think of the next property of the modulus of z to the n equals the modulus of z quantity to the n is sort of a generalization of the first property via induction. And these I'm going to have you prove on homework, so I'm not going to do them here. But you can prove these two properties just straight from the definition of modulus. As it turns out, though, there's an easier way to prove them once we start talking about complex conjugates, which is going to happen in this same lecture. But I think in the homework problem, you're to prove it just from the definition. Okay, so here's a sort of out of the blue fact that we're going to prove, but the reason we're proving it now is because it's a good exercise in playing around with moduli and things that we've learned so far. But it actually is important. It's an important fact for later when we go to prove the fundamental theorem of algebra. But here's what the fact says. So first of all, just suppose you got yourself a polynomial. So polynomials are just sums of powers of z, right? So the a0, a1, a2, all the way up to an, those are all complex numbers. The ai's are complex numbers. So this is a complex polynomial. And it's of degree n, so that nth term, the z to the n, the coefficient there is not 0, so that we can say that we've got a true nth degree polynomial. So here's what we're wanting to prove, that if we take the modulus of the reciprocal of that polynomial, it'll always be less than or equal to this 2 over the modulus of the nth coefficient times r to the n, whenever z is bigger than this r. So we want to prove that there exists such an r for which, so that this equation is true, or this inequality is true, whenever your z's modulus is bigger than r. So it's kind of a convoluted looking statement to prove. So I wouldn't worry too much about what it means in some sort of geometric sense or anything like that for now. I would just think of it as some sort of algebraic thing that we need to settle. So how can we go about doing this? Well, this involves a little trick at the beginning. So magically, for no obvious reason, we're going to consider this complex number w, which will be a naught over z to the n plus a1 over z to the n minus 1, and so on here, all the way until you get to a sub n minus 1 divided by z. So notice that this w does not have a constant term. All the terms involve a z in the denominator. So check out what happens when you multiply w by z to the n. Multiplying that expression by z to the n clears fractions, right? And so you end up with a0 plus a1, and then there'll be 1 left over z, then a2, and you'll have 2 left over z's, and so on, until you get to that last term. And you'd have a n minus 1, z to the n minus 1. If I just add, notice that this looks very much like the original polynomial p of z, highlighted in blue at the top. It's just missing the nth degree term. So let me take that equation that I have right now and add a sub n times z to the n to both sides. All right, so now what I can say is, like, look, the right-hand side here is the original polynomial p of z. So what we got here is p of z equals, and then on the left-hand side, I could factor out that z to the n, and I'd have w plus a sub n times z to the n. Why am I going through so much trouble here to write p of z in this alternate form? Well, it's because this breaks p of z into two separate quantities that I can individually consider in terms of modulus. So it just makes analyzing the modulus of p of z a little easier to break it up like this. So now let's take a look at the modulus of wz to the n, which you can see right up here, right? So what we're really talking about here is, the modulus of a0 plus a1z, all the way up to an minus 1 z to the n minus 1. On the left-hand side, remember we had this property that says when you're taking the modulus of the product of two complex numbers, you can write that as the product of the moduli separately. On the left-hand side, I could apply the triangle inequality and say this is less than or equal to the sum of those individual moduli. And then I could break that up a little bit further on the right-hand side and write it as modulus w times modulus z to the n is less than or equal to modulus a0, modulus a1 times modulus z, all the way up to modulus a n minus 1 times modulus of z to the n minus 1. So what I'm going to do is now solve this inequality for w, or for modulus of w, by dividing both sides by modulus of z to the n. And we don't have to worry about dividing by 0 here, because in this theorem we're going to do it whenever z is bigger than some pre-prescribed value that we'll make sure is bigger than 0. So we'll know that z is not 0. So we don't have to worry about that. So anyway, divide both sides by z modulus z to the n, and you get modulus a naught over modulus z to the n plus modulus a1 over modulus z to the n minus 1. You should think a little bit about why that's true. So I'm taking advantage of the property that modulus of z with the to the n, where the n's on the inside, is the same as modulus of z to the n on the outside, like that. So I'm taking advantage of that property, and then I'm dividing, and then I'm canceling things as I go. So by the end here, I get to modulus of a n minus 1, and then I'll just have modulus of z in the denominator. Okay, so what next? So the next thing we're going to do is we're going to choose real number r sufficiently large so that each of the terms on the right-hand side of this inequality is less than modulus an over 2 times n whenever absolute z is greater than r. What? Well, in that inequality on the right-hand side, you've got n minus 1 terms there. So you're dividing by z, right? So as you make the modulus of z get bigger and bigger and bigger, all those terms are going to 0. So if I pick z, z with a really big modulus, all of those terms are going to be really close to 0. So I can make them less than the modulus of an over 2 times n, because the modulus of an over 2n is just some fixed positive number. So it's just the observation that each of those terms on the right-hand side up there are going to 0 as z gets large. Okay, so why did we want to do that? And why that term absolute an over 2 to n? Well, that term was chosen just to make things work. It was sort of a product of reverse engineering it. But in any event, let's just go with it. So what would that tell us? That tells us that the modulus of w would be less than or equal to, well, the first term's less than modulus an over 2n, and the second term is less than modulus an over 2n. All the way down the line, modulus an over 2n, and there were n such terms because the counting started at 0 and went up to n minus 1. So since there are n of them and they're all the same thing, that would be n times modulus an over 2n, and then that just equals modulus an over 2. So here's what we know. This is less than or equal to this in yellow. That's the part that we care about. Now, you may remember I said we were going to look at, well, we just need to connect this up back to the original polynomial, which we know has a connection to this w, according to this formula here. So now that we've got sort of a bound on that w, that's pretty much gives us the game. If we look at that modulus of an plus w, we can do the reverse triangle inequality on it and say that that's greater than the absolute value of the modulus of an minus the modulus of w. We know what the biggest that modulus of w can be. So inside that absolute value there, the largest we can subtract off is an minus 2, or modulus an over 2. So this would have to be bigger than modulus an minus modulus an over 2. And of course, all that comes out to just modulus an over 2. So the next little inequality that we built up here is that this expression is greater than or equal to an over 2. Now remember what p of z was, the polynomial. P of z, we could write it in the form an plus w times z to the n. So we can now take the modulus of that. That'd be the modulus of that, which is equal to the modulus of an plus w times the modulus of z to the n. And we know that that first term right there is greater than modulus an over 2. And what do we know about the modulus of z to the n on account of the fact that all of this stuff above was only true whenever z was bigger than r? Well, we know z to the n would have to be greater than r to the n. So this comes out to being greater than absolute an over 2 times r to the n. What's important here is that the modulus of our polynomial is greater than the term at the end. And so if you invert both sides of an inequality, it reverses the inequality. So I'd get 1 over the modulus of p to the z would be less than the reciprocal of the other side, which would be 2 over modulus an times r to the n, which I believe is what we wanted to prove. So you see in this sort of complicated argument, we were using a lot of properties of moduli that we previously discussed. And when we need to use this fact later, we'll have it on hand. We won't have to prove it at that time. Okay, back to something simpler. Complex conjugates. So we've already talked about conjugates actually. So when you form a conjugate, you just change the sign in the middle. So if I want to do the conjugate of z equals x plus iy, it's just going to be, we use this z with a bar on top for the notation, and it's x minus I times y. And geometrically, all it amounts to when you form the conjugate is that you reflect it over the x-axis. So in this first picture here, if I've got an arbitrary z equals x plus iy, so I'm just changing to a negative y, right? So it just does this. So this is z conjugate equals x minus iy. And similarly, like if you took the conjugate of 3 plus 2i, that would be 3 minus 2i. I've drawn 3 plus 2i there on the right-hand picture, and then there's its conjugate down there like that. Okay? And so here at the bottom of this page, I'm cataloging several different identities that involve conjugates. And most of them are completely trivial to verify. The first property says when you take the conjugate of z, you just get back z. Because all you're doing is you're negating the imaginary part twice. And so when you do two negatives, you get a positive, right? The modulus of the conjugate of z is the same as the modulus of z. And you can verify that pretty easily for yourself. It's because this is true. If you take the conjugate of a sum, it turns out to be the sum of the conjugates done individually. Same thing with differences. The conjugate of a product is the product of the individual conjugates. Same thing with division. The quotient, the conjugate of the quotient is the quotient of the conjugates. The next two are a little weird looking, but they're very easily verified just with simple algebra. But it turns out that you can express the real part of z as z plus z conjugate over 2. So, I mean, algebraically, just the argument something like this, like if z is x plus iy, then z conjugate is x minus iy. And if you put all that over 2, what do you end up with? Well, you see the iy's cancel, and you get 2x over 2, which is just x, and x is the real part. So a similar thing works with the imaginary parts. And then the z times z conjugate equals the modulus of z squared. Again, pretty easy to verify just with some straightforward algebra. So I encourage you, the viewer here, to go through and verify these for yourselves. I promise that they're all pretty straightforward. And if you run into any trouble, let me know. And actually, that last one that was in that list on the previous page, z times z conjugate equals the modulus of z squared, you can actually use it to obtain both of these inequalities involving moduli that we'd previously done. In fact, both of these, or the first one is a homework problem, but you were going to do it just from the definition of modulus. But using conjugates, you can do a much quicker proof. Let me give you that quicker proof. Let's just say for the first part. I think if I show you the first part, then you can do the second part by yourself. So if you write down z1 times z2, and then you multiply it times its conjugate, z1, z2 conjugate. On the previous page, we saw that when you take the conjugate of a product, you can write that as the product of conjugates. So you can write this as z1, z2, z1 conjugate, z2 conjugate. Then you can shuffle things around a little bit because you have commutativity in multiplication. So you can write this as z1 conjugate times z2, z2 conjugate, which in turn is modulus z1 squared, right, because of that property in red up there, times modulus z2 squared. But at the very beginning, what is that really equal to? At the very beginning, if I take z1, z2, and I think of that just as a single thing, and then I'm multiplying times that conjugate of the same thing, that's really just modulus of z1, z2, whole thing squared. So here's what we see. This thing is equal to this thing over here. And everything in sight is positive because we're talking about moduli, which are already non-negative, and then you're squaring them. So since everything in sight is positive, I can take the square root of both sides and not have to worry about plus and minuses. And I get modulus z1, modulus z2 equals modulus z1 times modulus z2. So, and you can do a similar thing with the quotients too. So I challenge you, it's not a super hard challenge, but you do this one. Just mimicking the method I used there. Okay, I think that's probably enough for today. Our goal for the next little while is just to start developing our skills and just working with complex numbers on a very, arithmetical sort of level. So we're not trying to do calculus yet, limits, all that fancy stuff. We just want to develop our skills and comfort level with just taking complex numbers and manipulating them algebraically and, doing arithmetic with them. And once we get that under control a little bit, then we'll feel good about moving into limits and derivatives and integrals and that sort of thing. Okay, I'll stop there. See you again soon. Bye.